Okay, hi. I'd like to talk about how preschoolers initially understand symbolic numbers and how we measure this knowledge and what's wrong with those measurements and what the consequences are with that measurement. And basically, the literature has a consensus about that infants can understand some sort of numerical information. But we believe that this information is limited. So either they can understand numbers that are small, and by small I mean smaller than 4, or they can understand larger numbers, but those numbers, that understanding or this representation is imprecise. And clearly adults and also older children can understand precise exact numbers and exact large numbers, and by large numbers I mean larger than 4. And around when children are about 4 years old, they start to understand this exact large numbers. And this is exciting not only from the viewpoint of numerical cognition, but also, more generally in other area, like we have seen in the exciting morning lecture, that this numerical understanding is an example of how we understand concepts initially. And we believe that this point, when the kids are around 4 years of old, is the base of human-specific high-level math knowledge. And so this is a critical phase in numerical understanding. Now, if we want to understand or want to see how kids develop, mostly we are using a very simple task, the give a number task. In this conference, we've seen quite a few posters about numerical cognition, and many of them were applying this task. Now, the task is very simple. So we put a pile of similar objects in front of the kids, like, for example, our lab uses small balls, and we are asking the kids to give me 2 balls, or we tell a specific amount. And the children will give you some amount. And usually we are measuring numbers between 1 and 5, and whether the kids can give you correctly or incorrectly those numbers, we believe that number is known or unknown. And usually we are using a specific procedure called titration method, and this is a very simple thing. So we start from 1, and we are asking larger and larger numbers, and when the kids start to fail, we'll get back to the previous smaller numbers, and when they are successful, we'll measure the next larger number. And with this method, we try to sort of track the limit of their knowledge. And it's believed that after up to a point, they know the numbers perfectly, and beyond that point, they will not know anything. Now, using this task, there's quite a rich description how numbers are understood initially, and this has been described first quite extensively by Wynn. Wynn was not the first one to use this task, but she was the first one to describe a lot of critical features of this task and this development. So using this task, we can see a specific pattern in children. First, they are sort of pre-numeric, in a pre-numeric stage, which means that they know the number words. They know that 1, 2, 3, 4, 5, 6, and so on. They know the labels, but they don't know what they mean. So if we are asking for a specific amount of balls, they will not be able to do that. And around the age of 3 years, they usually can give you 1 ball, but they will not be able to give you larger. So we term them 1 knowers. After a few months, they can also give you 2, but not larger ones, and so on. And we term those 1, 2, 3, 4 knowers as subset knowers, and the term comes from the simple fact that although they have a large counting list, so they know what comes after 5, 6, and so on, but in a given number task, they will not be able to give you the proper amount. And sort of magically, when they understand 4 or 5, there's some ambiguity in the literature, when exactly, but at some point, they will understand the cardinality principle, which means that they will understand that when you're counting a set, the last word you are saying, last number word, is the size of that set. And when they understand this principle, then suddenly they can use all the number words that are in their counting list. Now, like every other lab, we are using this task, and we use some modified form of this task, and we modified the task only for some practical reasons. So we wanted to make the data collection and automatic analysis easier, and we wanted to check the reliability of the task we are using. So we modified the task in two details. First of all, we were not using this titration method, so we didn't try to sort of tap the barrier of the kid's knowledge, but we asked all numbers in a specific range. And another modification was that we didn't stop at 5, but we also measured 6 because we wanted to see the reliability of the task. And it's believed that if someone knows 5, then they should know 6, or if they don't know 5, they shouldn't know 6 either. So that's what we were simply checking. And surprisingly, we could find two things. The first one was there was some gaps in the knowledge of the children. So, for example, we could see kids who knew 1 and 2 and 4, but not 3. This is surprising. And also, if you are using this titration method, you would stop at 3, and you will never learn that the kid also knows 4. So basically, based on the classic description, this shouldn't happen. And also, we could see 5 knowers. So there, we could see some kids who knew 5, but didn't know 6. This is quite surprising because, again, based on the classic description, this shouldn't happen because when children understand 5, they should also understand 6. And so to check those accidental findings more systematically, we made some specific experiments when we measured 3 and 4 years old preschoolers, and we asked numbers from 1 to 6, and all numbers were asked 3 times. And here's the result. Let me explain that. So this is a single chart, and the stuff you can see on the right is actually the bottom part of the stuff you can see on the left. And also you can safely ignore the orange part. And the rows are the single kids. So you can see sort of the raw data. Well, it's a bit processed, but sort of the raw data of every single kid we have measured, and they are ordered by the overall performance. What you can see in the, what you can see in the, magic. What you can see in the green part is the overall performance of those kids. So it's just a proportion of the trials where they could give the numbers correctly, and they are ordered by this amount. So this is a data-based ordering. It's absolutely neutral from the viewpoint of theories or models. Now, the interesting part is the red-green part. So for every single kid, every single line, you can see the correct response proportion for 1, 2, 3, 4, 5, 6. And green means perfect performance, and red means 0 correct responses, and the colors in between are the performance in between. And there are a few details you should note here. First of all, well, this will not be really surprising. There are noise in the data. So occasionally, you could see some reddish or greenish part in the red or green field, which is just accidentally didn't pay attention, or maybe accidentally they could give you the correct amount, although they didn't really know that number. Okay, this is boring. Now, the next one is also sort of boring because that's what we could expect, that there are 5 knowers, 2 knowers, and so on. So, for example, here you can see kids who know 1 and 2, and they didn't know 3, 4, 5, 6, so they are 2 knowers. Okay, this is just a classic finding. Now, what is interesting is that you can see some 5 knowers, and in this larger sample, you can see that you can see that repeatedly that there are kids who know 1, 2, 3, 4, 5, but they don't know 6. And it's not just noise, because you can see that systematically, and you can see that noise looks differently in this chart. So it's quite a reliable phenomenon. And the fourth thing is, and this will take us to the question of gaps. that you can see some gradual performance decrease. And as I mentioned, usually it is supposed that children know the smallest numbers, and at some point their performance will radically drop. And they know everything about 3 and they know nothing about 4. But here you can see quite a few kids, and I'm pressing a wrong button. So here you can see quite a few kids who know perfectly 1 and 2. They don't know anything about 6. And there you can see some in-between performance, okay? So it's not a sudden drop in the performance, but it's more gradual. Now, this gradual change and the noise together will explain why we could see some gaps initially. Just imagine, again, the numbers for a kid, and the performance. And let's suppose that there's some gradual decrease in the performance, and we add some noise to this data. And we also have some threshold, and based on the threshold, we initially said that a number is known if the performance is above that, and it's unknown if it's somewhere down. And there you can see that some gradual decrease with some noise will present you some gaps. Now, we also replicated this measurement with some different parameters, and we could replicate the findings, so it's sort of robust across a few parameters. And there are a few implications. The first one is simply methodological. So when we are measuring the knowledge of kids, probably we should use some modified procedure. And also because the knowledge is not, it's not a sudden change across numbers, but it's more gradual. Probably we should use some different indexes to describe the kid's ability. And as you could see from the line of question marks, it's not clear yet what would be the best solution. Now, the second important implication is that if we are using a modified method, then we will see quite a different pattern what's going on when children understand numbers. Now, this is critical because, all the former models or theories that tried to explain the pattern, they were trying to explain the wrong data. So this is essential. And third, if finally, we want to understand what's going on in the kid's head, and let me just highlight one example. One explanation says that children are learning those numbers slowly, and suddenly at 4 they will switch to another representation because they are using the object tracking system. And the object tracking system is a visual system. It can track a few objects, usually up to 4. And maybe the system is used to track small numbers, and that's why they will be subset knowers for a while. But if there are 5 knowers and 6 knowers, as we could see that repeatedly, then this model just cannot be correct. And a final note, I know that many of you who are interested in numerical cognition and measuring preschoolers are using this paradigm, and all of them, all of the researchers relying on those 2 papers by Karen Wynn. And they are nice papers. They describe a lot of new features, at that time, how children develop. But actually, those papers haven't tested a lot of things. Let me just highlight a few of them. So, for example, when she described that this change from subset knowers to cardinality principle knowers happens around the number 4, actually, in the first paper, in the 1990 paper, 4 was not even measured. And in the second paper, there was only one 4 knower. So can you imagine the whole rule in the literature that everyone is using from the last 2.5 decades relies on a single kid. And there's some justification why that kid was cardinality principle knower. It is just a footnote in the second paper, and there's no detailed description why that could be true. So actually there are quite a lot of open questions about this task and how to measure this ability. So my conclusion is that probably a lot of properties of this task should be reinvestigated again, or not just reinvestigated, but we should investigate it systematically for the first time, because it will give you some different developmental pattern, which will obviously influence what theories we can propose. And thank you very much for your attention. If you're interested in more details, you can find it on the website of our lab. And also, I'd like to thank the Central European University to organize this conference repeatedly. We are very sad that they are leaving, not the conference, as I've learned. And probably more importantly, we are sad that some of us are staying. Thank you.
Thank you. So, questions?
So, I mean, this is all very interesting, and I guess my question to you is, what is going on then? So, the description of the method, the data are the data. It seems to me like with that gradual drop-off, what you've got is something like a mashup of the approximate number system and the object tracking system, where you're looking at variability that's increasing as the numbers get larger. I don't at all disagree that this is in many ways a better method, but it seems to be answering a different question. And it seems to me like the initial given number task may have been helping children or emphasizing the successor function, or essentially the given number task tracks with counting in a way that masks exactly what you found here, which is variability with number representation. So I guess that's just a long-winded way of asking you what is going on then.
Okay, on one hand, I agree with you that this modified version will not give you radically different results. I mean, there are cases where the modified version and the classic version will give you the very same results. But on the other hand, there are critical differences. And for one example was, the question of whether there are 5 and 6 numbers, because it will give you completely different possibility what theories you might apply here. And also, in other terms, for example, if you're using the titration method, then you believe that the performance will drop suddenly. And this is sort of theory or phenomena-driven way of measurement. And that's why, it's biased. And let me just give you another example why it could give you some radically different result at the end of the day. So there are a lot of validation tasks or studies showing that this knowledge measured with the classic given number task is correlating with a lot of conceptual knowledge. But if you think about those validation studies, all the time they can see some correlation which is far from perfect correlation. And on one hand, obviously, when we're working with children, there will be noise. So it's easy to explain. But on the other hand, there's always the possibility that maybe our measurement methods are not precise enough. So what I'm proposing here, partly, is that the previous method is not precise enough, and it includes some bias noise. And maybe if we are using some nicer methods, the validations could be more precise, and maybe we could see that some tasks are correlating much strongly, while other tasks are not correlating so strongly with this number knowledge measured with the given number task. So overall, this is just a small refinement on one hand, but on the other hand, it may have some more radical differences.
The last very short question, please.
Okay, so a short one. Well, I had one small comment, very small comment, that indeed I think you have 4 tests per number, right? And so it's hard to see here what the chance level would be really. So a lot of the gap, as you said, the gap that you see might just be noise. Also the smooth falling could be essentially noise. So I guess one question I have or a suggestion maybe is it would be interesting to take this gap numbers and maybe run other tests to really see if there are really gap knowers, or it's just that there's noise in the data rather than really not clear subset children.
If I understood you correctly, this type of displaying of the data is really informative in a sense, because you can see that really, you can see really the amount of noise and the gradual decrease for many kids like here. And with this sort of display of the data, you can sort of estimate the noise you could expect. Also, the random level should be some very low number, because very low value, because usually we are using a lot of balls in front of the kids, so we are putting like 30 balls, and we are asking only for a few. So if he or she does the job only randomly, practically he or she hardly could have a accidental hit. And if I understood you correctly, probably looking at those charts will tell you the answer.
Right, but it seems it seems to me that the global picture here is that there are still clearly subset knowers. The real thing where you differ from Karen Wynn maybe is that you have five knowers.
Oh, sorry, I couldn't understand.
The real difference, really, or the real novelty that you're proposing is that maybe there are 5 knowers. But otherwise, the global picture is that there are subset knowers and then CP knowers.
Sorry,
okay,
we'll discuss it later. I couldn't hear you.
Okay. Thank you again.
Thank you.
And